Okay, so we're going to do Newton's second law without friction. That's a little bit of a stretch. There is going to be some friction, and we'll try to account for that in the uncertainties. But here's the setup. We have a ramp, a pulley, a cart, a string, and we're going to have some hanging mass. So we'll actually hang the mass off the pulley, and we'll allow the mass to fall and pull the cart up the incline. One of the things that you're going to have to do is you're going to have to calculate the angle. Well, you're actually going to have to set the angle, okay? So we're going to do that the same way we did with the air track. You just measure the height, and by knowing the height, and these are values that I'll send you. So you'll measure the height. By knowing the height and the hypotenuse, you can calculate the angle. All right, so one of the things that we need to do is we need to know the mass of the cart. So here's the cart. I'll put it on the scale, and I'll weigh the cart, and I'll give you the mass of the cart. Then we have an extra mass that we'll add to the cart. This will make the cart roughly twice the mass of the cart by itself, because this extra mass is about the same mass as the cart. So I'll also give you a mass for this extra mass. Okay? Then one of the things that we're going to do is we're going to need to know this balancing mass. So I want to know statically how the cart, I want it in equilibrium where the hanging mass is balancing the cart. So the cart is still. It's not going uphill and it's not going downhill. Okay, so let me, and this should be determined experimentally, and I'll try to, of course I'm going to send you this data. Let's see, that was too much. This is still too much. So I'll go with a 20. Okay, I think I've got a little too much here. Oh, that's too much. Okay. Well, this is a little bit of trial and error. Okay. All right, that's pretty good. So I'm going to go to the center of the track. So I need just a tiny bit more mass. I've got a 10 here. That's a little too much, okay? So I will send you a value for M2 balance, but this one's around, let's see what I've got on here, 150 grams, okay? And once we have balance, then you can do the calculations, and I'll talk about the calculations next. Okay, so let's talk about the calculations that we're going to have to do, and you've seen some of these in the class already. So this is the setup. This is the mass of the cart, the little light string, and the hanging mass M2. When you read the procedure, you'll see these variables in the procedure, and of course the angle theta. So here's a free body diagram for the cart. There's a tension, mcg sine theta downhill, and then of course the normal force and mcg cosine theta normal to the ramp. We're not concerned about the normal force and the gravitational force on the ramp because we're ignoring friction. If next lab that we do, where we do Newton's second law with friction, we will be concerned about these things. Then for the hanging mass, all you have is the tension and M2G. I'm not going to show the derivation of how to get to this equation. We'll do it in class, or we have done it in class. So you get that the theoretical acceleration is m2 minus mc sine theta. That's the difference in these masses, divided by the total mass of the system, which is m2 plus mc, all times g. So in a perfect world, that should be what the acceleration is for the cart. Now, how did I find balance? What I did for balance was I played around with m2 until I got something that was very, very close, or should have been very close to mc sine theta. So I want this numerator to equal 0. And that's something that you'll check in your calculations. When I send you the mass of the cart and the balancing mass, you will check that. So m2 balance should be pretty darn close to mc sine theta. The next thing we're going to do is we're going to run the cart uphill. So to calculate the theoretical acceleration going uphill, we'll have m2, that's the hanging mass, minus m2 balance, that's the balancing mass that I just found, divided by the total mass of the system, times g. And we'll go back to the experiment and I'll show you how we'll run that, and then we'll come back and I'll show you how to do those calculations. Okay, so back to the ramp. So what we're going to do now is we're going to add some mass to the hanging mass. So that will be m2. We're going to add about 30 to 50 grams of mass to m2 balance. So let's say m2 balance was 230 grams, just as a simple case. Then maybe I want to add 30 more grams, so that would bring it up to 260 grams. So we have an unbalanced force here. m2 is going to fall and the cart is going to go uphill. We're going to time this. I'm going to start the cart. I know it's difficult to see, but I'm going to start the cart from this lower line and stop it at this upper line. That distance is 0.8 meters. Okay? So by knowing that distance and the time it takes, I'm going to time it, I can calculate the acceleration. You're going to do 3 runs. I'm going to give you some different scenarios, 25 degrees and cart plus extra mass, and you'll see that when I send you the data set, and it's in the procedure. But okay, I'm just going to do 1 run here just to show you how it goes. So your lab partner would be timing it, and you'd start 1, 2, 3, go, and you run it up till it hits there. And you time that, and then we'll do that 2 more times and take an average. So I'll show you on the board how those calculations go. Okay, so here's the calculations for the acceleration based on the times that we took and that distance, 0.8 meters. We know from what we've done in class that the constant acceleration equation is x equals 1/2 at squared plus v0t plus x0. These 2 terms are 0. We started from rest, and I'll call the starting point 0. So we have x equals 1/2 at squared. X is equal to 0.8 meters. We took 3 times. So I'm going to call t experimental T1 plus T2 plus T3 divided by 3, simply the average time. Okay? One thing that I want to add into this is the so-called reaction time. When you're timing the cart, there is a reaction time for the stopwatch. Over time, with different students and different classes, surprisingly, the reaction time is pretty darn fast, about 1/10 of a second. So we'll call delta t, or let delta t equal 1/10 of a second. So A plus, what I'll call A plus experimental, is 2 times 0.8. That comes from solving this equation. That's that distance x, divided by t experimental plus delta t. Delta t is 0.1 seconds, quantity squared. Then you'll calculate A minus experimental. That's the same thing, 2 times 0.8 meters divided by t experimental minus delta t, quantity squared. That gives you a range for your experimental acceleration. The idea is, does the theoretical acceleration that we calculated over here, does that fall in this experimental range? Sometimes it does. If it doesn't, you can talk about why it doesn't. So you'll talk about the uncertainties in that experimental setup. Okay?